For Unit 4, Notes 5, we will be discussing intermolecular forces. There are two types of forces that exist. Intramolecular forces, which occur inside of a molecule and hold it together. Examples include ionic, covalent, and metallic bonds. These forces are very strong. On the opposite end, we have intermolecular forces. These occur between molecules. They are much weaker. This image is a great example of how these two forces are different. Inside of our molecule, between the hydrogen and chlorine, exists an intramolecular force, our covalent bond, which is very strong and holds it together. Between two hydrogen-chlorine molecules, we have an intermolecular force, which is weaker. There are four types of intermolecular forces, the strongest being ion-dipole, hydrogen bonding, dipole-dipole, and the weakest London dispersion forces. London dispersion forces are temporary attractive forces that result when electrons in two adjacent atoms occupy the same position, making one end temporarily positive and one end temporarily negative. They occur between nonpolar molecules and atoms. They are the weakest, but they do become stronger if the mass increases. Dipole-dipole forces are attractive forces between the positive end of one molecule and the negative end of another molecule. They occur between polar molecules. They are much stronger than London dispersion forces, and the strength of the bond increases as the dipole moment increases. Hydrogen bonding occurs when the positively charged hydrogen end of one molecule is attracted to the negatively charged end of another molecule. This molecule must contain an oxygen, nitrogen, or fluorine. It is very similar to the dipole-dipole force, but is much, much stronger. Ion-dipole forces are generated between a polar molecule and an ion. They are most often seen when dissolving an ionic substance in water. For example, the positive sodium ion in salt would be attracted to the negative end of the water molecule. This is the strongest intermolecular force. When comparing the forces all together, ionic and covalent bonds, your intermolecular forces are the strongest. Then ion-dipole, hydrogen bonding, dipole-dipole, and the weakest London dispersion forces, which are all intermolecular forces. How do we know what forces will occur between a molecule? If we have an ion in a polar molecule, we know it's ion-dipole. If we have a hydrogen bonded to a nitrogen, oxygen, or fluorine, we know it's hydrogen bonding. If our molecule is polar, dipole-dipole, and all molecules have London dispersion forces. But if our molecules are nonpolar, it will only have London dispersion forces. Let's review how we determine if a molecule is polar or nonpolar. First, we can either draw a Lewis dot structure. If a molecule is symmetrical and there are no lone pairs on the central atom, our molecule is polar. We could also find the difference in their electronegativity values. 0 to 0.5 is nonpolar, 0.6 to 1.9 polar. Let's try example number 1. First, we want to identify any ionic substances, a metal bonded to a nonmetal. Then determine with the remaining molecules which type of intermolecular forces exist between them. Rank them from strongest to weakest, remembering the strongest means a higher boiling point. Let's identify our ionic compounds first. We're looking for a metal bonded to a nonmetal. There are two of them, calcium chloride and sodium chloride. Between these two, which has the stronger forces? We want to look at their charges. Calcium is a +2, while sodium is a +1, making calcium chloride the strongest bond. Next, with the remaining molecules, I like to identify my hydrogen bonding first. So I'm looking for a hydrogen bonded to a nitrogen, oxygen, or fluorine. And there's one example of these, HF. This will be my next highest boiling point. With the remaining 4 molecules, I want to identify whether they're polar or nonpolar. F2 would have a difference of 0, and neon being by itself would also be 0, making them both nonpolar. The last two I want to draw their Lewis structure. PCl3 and SO2 have a lone pair, making them polar molecules. Finally, we want to rank the last 4 remaining molecules. The polar molecules will exhibit the stronger dipole-dipole forces, and the nonpolar ones will exhibit the London dispersion forces. Between similar types of forces, we want to look at their molar masses. A higher molar mass will mean a stronger bond. PCl3, then SO2, and finally F2 and Ne. Let's summarize the forces acting on our molecules. Our two ionic compounds will exhibit ion-dipole forces, HF will exhibit hydrogen bonding, the two polar molecules will exhibit dipole-dipole forces, and the two nonpolar molecules will exhibit London dispersion forces. Remember, all molecules will have London dispersion forces. We can use intermolecular forces to determine a molecule's state of matter. Ionic compounds tend to usually be solids, while covalent molecules are usually gases or liquids. Things with hydrogen bonding are more likely to be liquids, and things that exhibit London dispersion forces are more likely to be gases, with a dipole-dipole being in the middle. Let's go back to example number 1 and predict the physical states of these molecules. Our two ionic compounds are going to be our solids. Our hydrogen bonding HF will be a liquid. Our higher massed dipole-dipole molecule will also be liquid, leaving the remaining 3 smaller molecules as gases. Let's try example number 2. Pause the video and rank the following molecules in order of decreasing boiling point based on their intermolecular forces, and then predict their states of matter.